Welcome back, applied calculators. This is the big one. This is the thing we have been marching toward all semester long. This is the fundamental theorem of calculus. The fundamental theorem of now, the fundamental theorem of calculus actually has two parts to it. We only concern ourselves with one of the parts because we are an applied calculus class. There's another part that's super important to students who are in Calculus 1 in some institutions somewhere, but not to us. We're not going to focus on that. We're going to focus on the thing that says, let f be continuous on the closed interval AB, and we require f to be continuous so that it can be integrated. It's a convenient way to go. Then, if you are looking for the definite integral from a to b of f of x dx, if you are looking for the area bounded by f of x in the x-axis, where f of x is above the axis, the things we've been talking about. If you're looking for the definite integral from a to b, you can do that by taking some antiderivative of little f, evaluating at b, that same antiderivative and evaluating at a, and then subtracting the answers. Where capital F is any antiderivative of little f. That's the idea. We find some antiderivative of the little f, we evaluate at the right endpoint, we evaluate at the left endpoint, and subtract those answers. So, if we're looking for the integral from 1 to 3 of 2x dx, and just a reminder of what that means, here's the function 2x, there's x equals 1, there's x equals 3. We're looking for this area. We can find that area by taking an antiderivative of 2x and what the notation will say, evaluating between 1 and 3. And that just means we substitute 3, we substitute 1, and subtract the answers, and that's 8. Now, you and I could independently verify that the area of this trapezoid over here is 8. We could verify that, and that's important, but it's not going to be helpful to us when we try to find the integral from 1 to 3 of x squared dx, because I don't know how to find this area geometrically. I only know how to find this area with the calculus. And the calculus says I find some function whose derivative is x squared. I'm going to choose this one. We evaluate at 3, we evaluate at 1, and subtract the answers. So this is 1/3 of 3 cubed minus 1/3 of 1 cubed, and that turns out to be 26/3. The fundamental theorem of calculus says we take any antiderivative, evaluate at the right endpoint and the left endpoint, subtract the answers. That's the whole thing. That's the whole thing. So what does that mean? That means we could do this. Now, to be clear, here's 1 over x. Here's x equals 2. Somewhere out here is x equals 8. It's this area we're interested in. That's the area. So what do we do with that? Well, we find some antiderivative of 1 over x. Wait a minute. We have that. We evaluate, and subtract. Well, that means natural log 8 minus natural log 2. We evaluate at the right endpoint and the left endpoint and subtract the answers. Now, I'll leave it up to you to think about. If you were to check the so-called back of the book on something like this, you would find the answer printed this way. And I've got to give you a moment to think about why this should be printed in the back of the book like this. I mean, it takes up less space, so that's the reason for that. But what's the property of logs that allows us to go from here to there? As we're getting ready for final exam, we've got to know properties of logs. I'm going to do one other thing in this video before we do the other thing in the other video. Let's do the integral from 0 to 4 of x squared minus 4 dx. Now, nothing fancy here. Nothing fancy at all, right? We're going to find an antiderivative. We're going to substitute, and subtract, right? Antiderivative of this thing. I don't think I'm out of school here. And so we're going to substitute the 4. We're going to substitute the 0 and subtract those answers. So what's that? That's 64 thirds minus, that's 16, that's 48 thirds, that's 16 thirds. Now that's going to feel a little weird when you get a look at the picture, right? Like here's the picture. But here's the deal. Some of this area is above the axis and some of this area is below the x-axis. So what does that mean? That means that this 16 thirds is the difference between the area above the axis that's got a positive integral value and the area below the x-axis that's got a negative integral associated with it. This 16 thirds means that there's 16 thirds more units of area above the axis than below. That's an important thing for you to remember. I'm going to do a second video that has some more examples if you need the more examples. Otherwise, I look forward to seeing you in class.